Welcome to today's session. We're diving into an exciting problem titled Trapping Rainwater 2, which focuses on finding the maximum amount of water that can be trapped in a 2D grid. This problem is a challenging variation of the well-known trapping rainwater problem and has applications in computational geometry and optimization. Let's explore the approaches step by step. The problem we are tackling is called Trapping Rainwater 2. Imagine we have a 2D elevation map represented as an MXN matrix called height map. Each cell in this matrix has a value that represents the height of the terrain at that location. After it rains, water can collect in the low-lying areas surrounded by higher elevations. Our task is to calculate the total volume of water that gets trapped on this elevation map. The input to the problem is this height map matrix, where the dimensions of the matrix heightmap.length and heightmap0.length can range from 1 to 200. Additionally, the height values for each cell, heightmap I, j, are integers between 0 and 100,000. The output will be a single integer representing the total volume of trapped water. Now, let's look at an example to clarify how this works. Consider the first example. The input height map is a 3x6 grid, and the height values are provided in the matrix. After it rains, water collects in the low-lying areas. For instance, at cell 1, 1, the surrounding elevations are higher, so 1 unit of water is trapped there. Similarly, at cell 1, 2, 2 units of water are trapped because the surrounding elevation allows it. Finally, at cell 1, 4, 1 unit of water is trapped. When we add up all the trapped water, we get a total of 4 units. This demonstrates how the trapped water is calculated based on the difference between the height of the basin and the minimum surrounding elevation. Let's examine one more example to solidify this concept. In the second example, the height map forms a 5x5 grid. Here, the terrain creates an inner basin surrounded by higher elevations. After it rains, water collects in the central area. For example, at cell 2, 2, 2 units of water are trapped because the surrounding height is 3, and the cell's height is 1. Similarly, other inner cells trap 2 units of water each. When we calculate the total, the inner basin traps 10 units of water altogether. This example shows how the algorithm must consider all low-lying areas and calculate the trapped water accurately while taking the surrounding heights into account. Now, let's look at some additional constraints and edge cases to keep in mind. There are a few important considerations for this problem. First, when dealing with edge cases, a completely flat elevation map, where all heights are the same, won't trap any water since there are no basins. Similarly, if the matrix has only a single row or a single column, no water will be trapped as there's no way to form closed boundaries. For larger grids, such as a 200 by 200 matrix, the solution must be efficient both in terms of time and space to handle the computation within reasonable limits. Lastly, it's important to note that edge cells, those on the boundary of the matrix, cannot trap water because they don't have all 4 sides enclosed. These constraints help define the scope of the problem and guide the implementation of the solution. To solve the problem of trapping rainwater in a 2D grid, we first considered the brute force approach. The intuition here is straightforward. For each cell in the grid, we calculate how much water it can trap by examining the minimum height of its neighboring cells in all 4 directions. If the minimum boundary height is greater than the cell's own height, the difference between these values represents the trapped water at that cell. However, this method requires scanning all neighbors for every single cell, which leads to multiple passes over the grid. This makes it computationally expensive. Specifically, the time complexity is O, open parenthesis m times n close parenthesis squared, since for each cell we examine all its neighbors. The space complexity is O1, as no additional data structures are used. While intuitive, this approach is highly inefficient for larger grids due to its nested loops, making it unsuitable for competitive programming or real-world scenarios where performance is critical. To address these inefficiencies, we explored an optimized approach using a min-heap, or priority queue. The optimized approach takes a more systematic and efficient path to solve this problem. Instead of iterating through all cells, we focus on the boundary cells first, since these cells cannot trap water themselves but serve as the limiting walls for interior cells. Using a min-heap, we start by adding all boundary cells along with their heights into the heap. To ensure no cell is processed more than once, we use a visited matrix. Then, we repeatedly extract the smallest height cell from the heap and examine its unvisited neighbors. If a neighbor's height is smaller than the current boundary, it means water can be trapped there, and we calculate the water volume. Next, we push the neighbor to the heap, updating its boundary height to the maximum of its current height and the neighbor's height. This ensures the boundary heights dynamically adjust as we process the grid. This approach is much more efficient, with a time complexity of O(m*n*log m*n) due to the heap operations and a space complexity of O(m*n) for the heap and visited matrix. While it uses slightly more memory, it is substantially faster than the brute force approach, making it more practical for larger grids. After evaluating both approaches, we chose the optimized min-heap method for its balance between efficiency and clarity. This strategy prioritizes boundary-first traversal, ensuring that water trapping calculations are always based on the smallest boundary heights. By doing so, we reduce redundant checks and improve the overall efficiency of the solution. The time complexity of O(m*n*log m*n) makes this approach scalable, even for large grids. The brute force method, while simpler to understand, proved too computationally expensive and impractical for real-world datasets. One of the key insights, or the aha moment, was realizing that the trapping process naturally follows the principle of processing the smallest boundary first. This understanding made it clear that a min-heap was the ideal data structure to manage the dynamic updates to boundary heights efficiently. Ultimately, the min-heap approach stood out for its scalability and systematic nature. While it does require more memory than the brute force strategy, the significant reduction in time complexity makes it the optimal solution for this problem. In this problem, we are tasked with calculating the total amount of water that can be trapped after rainfall on a 2D height map, which is represented as a grid. Each cell in this grid indicates the height of the terrain at that point. Our goal is to determine how much water can accumulate across all cells of this grid. To solve this efficiently, we use a priority queue, also known as a min-heap, combined with a boundary-first search approach. This method processes the grid starting from its outermost boundary and works inward, dynamically calculating the trapped water at each step. The first step involves initializing the priority queue and a visited set. Here, we add all the boundary cells into the priority queue, where each cell is represented by its height, row index, and column index. Simultaneously, we maintain a visited set to track cells that have already been processed. Then, we enter the main part of the algorithm, which is the processing of boundary cells through the priority queue. Within this step, while the priority queue is not empty, we extract the smallest boundary cell, which corresponds to the cell with the lowest height. From there, we explore each of its unvisited neighbors in all four directions, up, down, left, and right. If a neighboring cell has not been visited, we calculate the water trapped at that cell. This is determined by taking the maximum of 0 and the difference between the current cell's height and the neighbor's height. If water is trapped, we add this value to the total trapped water. Next, we update the neighbor's effective height to reflect the current boundary's height. This is done by taking the maximum of the neighbor's original height and the current cell's height. This adjustment ensures that the boundary is dynamically updated as we process the cells. The neighbor's cell is then added to the priority queue, and its coordinates are marked as visited to avoid redundant processing. This loop continues until all cells in the grid have been processed and accounted for. At the core of this approach is the idea of using a boundary-first search, which ensures that the trapping potential for every inner cell is dictated by the lowest surrounding boundary. This prevents overestimating the trapped water since the capacity of each cell depends on the heights of its neighbors. The priority queue plays a vital role here by guaranteeing that we always process the lowest boundary first, which is critical because the lowest boundary limits how much water can be trapped in the surrounding cells. Additionally, the algorithm dynamically updates the height of each processed cell to reflect its role as part of the boundary for subsequent calculations. This reduces the need to retraverse already processed areas. The visited set ensures each cell is only processed once, which prevents infinite loops and redundant computations. Together, these elements create an efficient and reliable way to calculate the trapped water across the entire grid. Now, let's discuss the data structures and complexity analysis. The priority queue, or min-heap, is used for efficiently retrieving the lowest boundary cell at each step. Operations such as insertion and extraction in the heap have a time complexity of O log n, where n is the number of cells in the heap. The visited set, on the other hand, tracks which cells have already been processed, ensuring that each cell is only handled once. Checking membership in the set is an O1 operation. When analyzing time complexity, processing each of the m*n cells involves a single heap operation, which gives a total time complexity of O m*n log m*n. The space complexity is also O m*n, because both the priority queue and visited set can grow up to the size of the grid. These complexities make this algorithm efficient even for larger grids. Finally, we'll walk through an example to solidify our understanding. Consider the input grid 1, 4, 3, 1, 3, 2, 3, 2, 1, 3, 2, 3, 2, 3, 3, 2, 3, 1. First, all boundary cells are added to the priority queue. These cells define the initial trapping potential. As we process the boundary cells one by one, we calculate the trapped water for each unvisited neighbor and dynamically adjust the boundaries to reflect the updated heights. This continues until every cell in the grid has been processed. In this example, the algorithm determines that the total water trapped is 4. This step-by-step approach, combined with the use of a priority queue and boundary-first search, ensures that the solution is both correct and efficient. To solve the problem of trapping rainwater in a 2D grid, we start by importing the Heap module for efficient heap operations. Then, we define the trap rainwater method within our solution class. The first thing we check is whether the height map is empty or invalid. If so, we return 0 immediately since no water can be trapped. Next, we determine the number of rows and columns in the grid, and we create a visited matrix to keep track of which cells have already been processed. Additionally, we initialize a min_heap to manage the boundary cells and their heights efficiently. Now, we add all the boundary cells to the heap. For this, we iterate through the first and last columns for each row, and the first and last rows for each column. These boundary cells act as the starting points for our algorithm, and we mark them as visited to avoid revisiting them later. Finally, we define the possible movement directions right, down, left, and up, as well as variables to track the total water trapped and the maximum height encountered so far. With these initializations in place, we are ready to process the heap. We begin processing the cells in the min_heap one by one using a while loop. For each cell, we pop the smallest height from the heap, which helps us simulate filling water level by level. We then update the max_height to ensure it reflects the highest boundary encountered so far. Next, we explore all 4 neighboring cells of the current cell using the predefined directions. If a neighboring cell is within bounds and hasn't been visited yet, we calculate the amount of water trapped at that cell. This is determined by the difference between the max_height and the height of the neighboring cell, ensuring that the difference is non-negative using the max0 function. After calculating the trapped water, we mark the neighboring cell as visited and push it onto the heap, using the greater of its own height or the max_height to maintain accuracy for future calculations. Once all cells have been processed, the total water_trapped value is returned, representing the solution to the problem. This algorithm efficiently computes the trapped water by combining a priority queue with breadth-first search principles. Here, we begin by importing the necessary libraries and defining our solution class along with the trap rainwater method. The first step is to handle edge cases where the input height map is null, empty, or has no columns. If any of these conditions are met, we simply return 0 since there's no terrain to trap water. Next, we calculate the number of rows and columns in the height map and initialize a visited 2D array to keep track of which cells have already been processed. We also create a min_heap, which is a priority queue that will help us process cells in ascending order of their height values. The next part of the code adds all boundary cells to the min_heap. This is because water can only be trapped inside the boundaries, and we start by processing the outer edges first. For each boundary cell, we mark it as visited and add it to the heap. This ensures that we have a complete perimeter of the height map in the heap before moving inward. Now, we define the directions array, which represents the 4 possible movements right, down, left, and up. This will be useful for traversing the neighbors of each cell. We also initialize the water trapped variable to 0, which will store the total amount of water collected, and the max height variable to track the tallest boundary we've encountered so far. The while loop begins processing cells from the min heap, starting with the cell that has the smallest height. For each cell, we update the max height to ensure it reflects the tallest boundary we've seen as we expand inward. Then, for each of the 4 possible directions, we calculate the row and column of the neighboring cell. If the neighbor is within bounds and hasn't been visited yet, we mark it as visited and calculate the water that can be trapped at this neighbor. This is done by subtracting the neighbor's height from the max height, but only if the result is positive. We then add the neighbor to the heap, using the greater of its own height or the max height. This ensures that the heap always processes cells in the correct order to trap water effectively. Finally, we define the cell class, which is a helper class to represent each cell in the height map. This class has 3 fields: row, col, and height to store the cell's position and its height value. The constructor initializes these fields when a new cell object is created. By encapsulating the cell data in this class, we can easily manage and compare cells in the priority queue. Once all cells have been processed and the heap is empty, the water trapped variable will contain the total amount of trapped rainwater, and it's returned as the result. This completes the implementation, efficiently calculating the trapped water by leveraging a min heap and a breadth-first search approach. To solve this problem, we start by initializing the required variables. In this 3x3 grid, we have 3 rows and 3 columns. We create a visited matrix to keep track of which cells have been processed, initializing all values to false. Next, we add all the boundary cells of the grid to a min heap, along with their heights and coordinates. This ensures that we process the lowest boundary cells first. At this point, the heap contains cells like 1, 0, 0, 4, 0, 1, and so on, representing the boundary heights and their positions. We also mark all these boundary cells as visited. Once initialized, the algorithm proceeds by processing cells from the heap. The first cell popped from the heap is 1, 0, 0, which becomes our current max_height for tracking water levels. From here, we begin exploring its neighbors to determine if water can be trapped. When processing the neighboring cells, we look for unvisited cells and calculate whether water can be trapped based on their heights. For example, the neighbor below, 1, 0, has a height of 3. Since this height is greater than the current max_height of 1, no water is trapped, but we update the heap with this cell and mark it as visited. The heap now has entries like 3, 0, 2, and 2, 2, 0, and the process repeats for all other cells. During this iterative process, any low-lying neighbors below the max_height contribute to the trapped water. For this grid, after processing all cells, we calculate the total water trapped as 2 units. This approach ensures we account for all potential low points surrounded by higher boundaries. For a larger 4x4 grid, the process is similar. We initialize the rows, columns, and the visited matrix, and add all boundary cells to the min heap. As we process the heap, we explore the neighbors of each boundary cell. Here, the internal cells, 1, 1, and 2, 2, are completely surrounded by higher boundary cells. To calculate the water trapped in these internal cells, we use the formula min, max_height, boundary height, cell height. For both 1, 1, and 2, 2, the trapped water is 3 units per cell, as the boundaries are at height 4, and the cell heights are 1. After processing all cells, the total water trapped in this grid is calculated to be 6 units. This demonstrates how the algorithm efficiently handles grids with internal basins surrounded by higher boundaries. In the case of a flat surface, the grid has uniform heights for all cells. Here, we initialize the rows, columns, and the visited matrix as before, and add all boundary cells to the min heap. However, as we process the heap, we find that no neighboring cells have heights lower than the max_height, since all cells are at the same height of 3. This means no water can be trapped in this grid. After processing all cells, the total water trapped remains 0. This serves as an edge case where the algorithm confirms that no water can accumulate on a perfectly flat surface. To analyze the time complexity of this algorithm, let's break it down into 2 main parts. First, during heap initialization, all boundary cells are pushed into the min heap. Since there are approximately 2 rows plus 2 cols for boundary cells, this step takes rows plus cols time. Adding each of these boundary elements to the heap requires O log k time, where k is the number of elements in the heap. In this case, k is at most O rows plus calls, so the heap initialization step is efficient. Next comes the heap processing phase, which is the core of the algorithm. Here, every cell in the grid is added to the heap exactly once. For a grid of size rows asterisk calls, this results in O rows asterisk calls operations. For each of these operations, the heap performs insertions or removals, which take O log n time, where n is the size of the heap. The heap grows to at most the total number of cells in the grid, i.e., rows asterisk calls. Therefore, the total cost of heap operations is O rows asterisk calls asterisk log rows asterisk calls. When we combine these steps, the overall time complexity is dominated by the heap processing phase, resulting in O rows asterisk calls asterisk log rows asterisk calls. Now, for the space complexity, there are two major contributors. First, the algorithm uses a visited matrix to track which cells have already been processed. This matrix has the same dimensions as the grid, so it requires O rows asterisk calls space. Second, the min heap stores at most one entry for every cell in the grid. In the worst case, this means the heap will occupy O rows asterisk calls space as well. Apart from these, the algorithm uses some additional variables like directions for movement, and max underscore height and water underscore trap to maintain state, but these require only constant space, or O1. When we sum up all these components, the total space complexity becomes O rows asterisk calls, which is directly proportional to the size of the input grid. Let's compare this optimized approach with the brute force method. The brute force approach involves repeatedly iterating over all the cells in the grid to calculate the trapped water. For each cell, it checks the maximum height of the boundaries surrounding it, leading to a time complexity of O rows asterisk calls 2 due to the repeated scanning. By contrast, the current optimized approach makes use of a priority queue, or min heap, to process each cell only once. This ensures efficient access to the smallest boundary height at any given time, reducing the time complexity to O rows asterisk calls asterisk log rows asterisk calls. Looking at different scenarios, the time complexity remains the same across best, average, and worst cases. In the best case, where all heights are equal and no water is trapped, all cells are still processed, and the complexity remains O rows asterisk calls asterisk log rows asterisk calls. In the average case, with random heights, the algorithm calculates water trapping efficiently using the heap structure. Even in the worst case, involving highly uneven heights, the heap operations still adhere to the same complexity. This consistency highlights the robustness of the optimized approach. Finally, let's understand the mathematical reasoning behind the big O complexity. The rows asterisk calls term arises because the algorithm processes every cell in the grid exactly once. Each cell is evaluated for its ability to trap water, and this contributes linearly to the time complexity. The log rows asterisk calls term comes from the heap operations. Every insertion or removal in the heap is logarithmic with respect to the number of elements in the heap, which grows to at most rows asterisk calls. Combining these two terms, we get the overall time complexity of O rows asterisk calls asterisk log rows asterisk calls. This mathematical proof solidifies our understanding of why the algorithm is both efficient and scalable for large grids. When tackling this problem, there are several common mistakes to watch out for. First, misunderstanding boundary conditions is a frequent issue. Remember, the edges of the grid cannot trap water because they don't have enclosing walls on all sides. Overlooking this can lead to an overestimation of the total water trapped, which in turn results in an incorrect solution. Another pitfall is failing to differentiate between local and global heights. It's important to understand that the water level at any given cell is influenced by the global boundary heights in all four directions, not just the immediate neighbors. Ignoring this can lead to underestimating the trapped water, as distant boundaries often play a critical role. Efficiency is another area where mistakes are common. A brute force approach, such as using nested loops to calculate trapped water for every cell, may seem straightforward but is computationally expensive and infeasible for larger grids due to its m²*n² time complexity. Lastly, the choice of data structures is crucial. Using arrays instead of more dynamic structures like priority queues can make the solution inefficient or unnecessarily complex. Selecting the right tools for the job is key to implementing an optimal algorithm efficiently. Edge cases are another area where mistakes are often made. For example, grids with all heights equal, empty grids, or very small grids like 1 by 1 or 1 by 2 can behave differently and must be carefully tested. Ignoring these edge cases can lead to runtime errors or incorrect outputs, which can be especially problematic during an interview. Speaking of interviews, there are some valuable insights to keep in mind. This problem is a 2D variation of the classic trapping rainwater problem, so understanding the intuition behind boundary heights is critical. The optimal approach typically involves using a priority queue, or min-heap, to simulate a flood fill process. This achieves an efficient time complexity of O, m*n*log, m plus n, making it well suited for larger grids. During interviews, expect to be tested on how well you understand dynamic boundary updates and efficient height tracking. It's not just about writing the code but also being able to explain why your approach ensures all trapped water is accounted for and how it handles edge cases. This problem also has several related problems that can help deepen your understanding. For instance, trapping rainwater, LeetCode number 42, is the 1D version of this problem, where the focus is on arrays instead of grids. Then there's max area of island, LeetCode number 695, which is another flood fill problem but focuses on identifying connected components. Pacific Atlantic water flow, LeetCode number 417, is another interesting challenge that involves simulating water flow to determine reachability. Now, when it comes to alternative approaches, there are a few you should consider. The brute force method, while simple, calculates trapped water for each cell by iterating through all boundary heights, which results in an O, m squared asterisk n squared complexity and is generally too slow for larger grids. A dynamic programming approach precomputes the maximum boundary heights in all directions for each cell, trading off space for improved time efficiency with an O, m asterisk n complexity. However, the most optimal approach is using a priority queue, which dynamically tracks boundary heights during a flood fill process. This method achieves O, m asterisk n asterisk log, m plus n, complexity and is the best choice for solving this problem efficiently in most cases. Each approach has its trade-offs in complexity and implementation difficulty, so understanding the constraints and time available will help you decide the best method during interviews. Great job making it to the end of this problem. Today, we learned how to solve trapping rainwater 2 efficiently using advanced techniques like priority queues. Remember the importance of balancing time and space complexity, and apply these takeaways in similar problems. Thanks for watching, and don't forget to like and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!